Imagine trying to build a futuristic city in a place where the first problem is not traffic, it is not housing, it is not skyscrapers, it is water. For years, NEOM has been sold as one of the boldest construction visions on Earth. A new region on the Red Sea, a mirrored linear city cutting through the desert, new ports, resorts, industries, and communities built almost entirely from scratch in northwest Saudi Arabia. But every render hides the same question: where does the water come from? Because in this part of the world, water is not something a city simply receives from nature. It has to be produced. It has to be powered. It has to be moved through long pipelines. It has to be stored, recycled, monitored, and protected. And whatever is left behind has to be controlled before it damages the very sea that made the whole project possible. That means NEOM's most important megaproject may not be the line. It may be the invisible machine beneath it. Desalination plants, renewable power, reservoirs, pumping stations, wastewater recycling, and brine treatment. And if that machine falls behind the city's ambition, the future does not simply slow down, it runs dry. This is the story of NEOM's $500 billion desert city, and the water system that decides whether it becomes a model for the future or the world's most expensive mirage. Before we get into the system, we have to separate the dream from the plumbing. NEOM is not one building, it is not even one city. It is a planned region on the northwest coast of Saudi Arabia along the Red Sea, designed to include several major developments: the Line, Oxagon, Trojena, Sindala, Magna, and the infrastructure needed to connect them. The most famous piece is the Line, a proposed linear city stretching 170 kilometers, only 200 meters wide, and rising 500 meters above sea level. It is the image everyone remembers: two mirrored walls cutting through the desert like a blade. But NEOM is bigger than that single image. It includes industrial zones, coastal tourism, mountain development, ports, energy projects, airports, roads, utilities, and a whole new economy that Saudi Arabia wants to use as part of its post-oil future. The marketing language is seductive: renewable energy, walkable neighborhoods, zero-emission transit, artificial intelligence embedded into daily life, advanced manufacturing, a new relationship between cities and nature. But all of that depends on something much older than any smart city: a reliable water cycle. And this is where NEOM's story diverges from almost every traditional city. Most cities grow around water: rivers, aquifers, reservoirs, lakes, seasonal rainfall, snowmelt, or regional supply networks usually arrive first, and the city organizes itself around them. Even cities in dry climates often inherit something: groundwater reserves, imported water systems, older reservoirs, or decades of existing pipes. NEOM is different. It is being built in one of the driest regions on Earth, where natural freshwater is extremely limited. Rainfall can be measured in only a few dozen millimeters in many years, and there are no permanent rivers to build around. So the water plan is not a supporting document inside the master plan. It is the master plan. Because a city can postpone a museum. It can delay a district. It can redesign a tower, cut a hotel wing, or move a stadium entrance. But it cannot negotiate with daily water demand. The moment people move in, hotels open, construction work accelerates, and industry starts operating, the system has to behave like reality, not like a plan in a book. The taps have to open. The toilets have to flush. The cooling systems have to run. Construction dust has to be suppressed. Emergency reserves have to be ready before the emergency arrives. That is why water is the perfect test of NEOM. Strip away the glass facades, the price tag, the geopolitical ambition, and the architectural renders, and what remains is a simple, ancient, unforgiving question: Can enough water be made, moved, stored, and reused reliably every day at city scale in one of the driest places on Earth? NEOM cannot simply find that water. It has to manufacture it. And that is the first revelation. NEOM's water supply is not a source. It is a factory. NEOM's own water plan is built around desalination powered by renewable energy. In simple terms, seawater from the Red Sea is pulled into a treatment system. Dissolved salts are removed through advanced filtration and membrane processes, and fresh water comes out the other side. On a diagram, it looks clean. Sea in, fresh water out, city supplied. But in a desert at city scale, that simple diagram becomes one of the most demanding industrial operations on the planet. Because desalination is not a tap you turn on. It requires intakes that bring seawater in while limiting marine damage. It requires membranes, pumps, filters, chemicals, operators, monitoring systems, spare parts, maintenance crews, and continuous power. Then the finished water has to be moved inland through pipelines, pumped through pressure zones, held in reservoirs, protected from contamination, and delivered with enough reliability that a failure does not become a crisis. And then comes the part almost nobody puts in the render: brine. When you remove salt from seawater, the salt does not disappear. It becomes a concentrated leftover stream. And if that stream is handled poorly, it can raise local salinity near the discharge point and stress marine ecosystems. That matters because NEOM is not drawing from an empty bathtub. It is drawing from the Red Sea, a marine environment known for coral reefs and ecological value. So NEOM's plan does not treat brine as a detail. It treats brine as one of the central engineering problems. The idea is to process it, recover useful minerals and materials from it, and reduce the amount of waste that returns to the sea. NEOM has also promoted pilots, including brine-based concrete, and partnerships around brine valorization. That is ambitious. It is also the right problem to focus on. Because if NEOM is going to market itself as a sustainable desert city, it cannot simply copy the old model of desalinating water and pushing the difficult part out of sight. It needs a cleaner loop. That loop has 4 steps. First, make fresh water from seawater. Second, power the process with renewables. Third, recycle wastewater back into useful water. Fourth, manage or recover the brine so the Red Sea does not become the hidden cost of the city. If those 4 steps work, NEOM becomes a laboratory for future arid cities. But if one fails, everything gets harder. Because here, water is not just another utility. Water is life support. And life support has to work every day. That brings us to the second layer of the problem. Saudi Arabia already knows desalination. The kingdom is one of the world's great desalination powers, and desalinated water already supplies a major share of its domestic drinking water. So the question is not whether Saudi engineers understand how to remove salt from seawater. They do. The real question is whether NEOM can build a new version of desalination that is larger, cleaner, more integrated, and synchronized with a city that is still changing shape. That is much harder. The numbers are huge. NEOM has described a smart water network stretching hundreds of kilometers from coast to desert, major reservoirs, pumping stations, wastewater recycling, and brine processing built into the system from the beginning. It has also reported real progress. Transmission pipelines already laid, storage assets built, pumping stations installed, and potable water production already operating. So this is not just a concept slide. Parts of the water machine exist. But the distance between what is operating today and what a populated city demands tomorrow is the real story. A desalination-dependent megacity needs 3 things at once. First, it needs continuous power. If power supply falters, water production can falter with it. Renewable energy is not just an environmental promise here. it becomes the fuel line for daily life. Second, it needs redundancy. A normal city may be able to absorb failure through older networks, backup reservoirs, or regional water transfers. A new desert city has to design its safety margin from the start: storage reservoirs, alternate routes, spare capacity, emergency pumping, and the ability to isolate a failure before it cascades. Third, it needs timing. Water infrastructure has to arrive before demand does, not alongside it, before it. But megaprojects are always tempted by visible progress: the towers, the stadiums, the hotels, the transit systems, the images that prove momentum to the world. Pipes are not that image. Reservoirs do not go viral. Brine processing plants do not sell the dream. But without them, the dream is fragile. That is why recent reporting around NEOM matters. The long-term image of the line is a 170-kilometer city for millions of residents. But reporting has described a much smaller initial focus, with work concentrated around an early stretch and major event-linked deliverables. That does not mean the whole project is dead. It means the project is entering the discipline phase. And water infrastructure is where discipline becomes unavoidable. Because water does not care about master plans. It only cares whether the capacity exists when demand arrives. Now there is a second revelation hiding inside the shape of the line itself. Even if NEOM can make enough water, it still has to move that water through a city shaped like a spine. A traditional city is messy, but it is usually clustered. Water mains branch out, loop around neighborhoods, and create a network. If one area fails, another route may help. If demand spikes in one district, nearby systems can sometimes support it. The line is different by design. It is long, narrow, and linear. That geometry may save land. It may concentrate services. It may create new possibilities for transit, density, and energy distribution. But for water, it creates a supply chain problem. Imagine feeding a city through a long body. The source is near the sea. The city stretches inland. Every segment needs pressure, storage, monitoring, fire flow, drinking water quality, wastewater collection, and recycled water networks. A failure at one point is not just a local inconvenience. It can become a severance. So engineers need a spine with backup arteries. They need district storage nodes. They need pressure zones. They need sensors that can find leaks fast. They need valves that can isolate trouble without cutting off an entire district. And they need enough reserve that maintenance does not become a public crisis. This is the unglamorous side of futuristic urbanism. A linear city looks simple from the air. But under the surface, it may need one of the most carefully staged utility networks ever attempted. And construction adds another twist. NEOM needs water before NEOM is fully inhabited. Before millions of residents arrive, construction camps need water. Concrete work needs water. Dust suppression needs water. Workers need sanitation. Equipment needs cleaning. Temporary roads, batch plants, landscaping trials, ports, and early tourism assets all create demand before the city produces revenue at scale. That means the water machine has to grow ahead of the city, not alongside it, not behind it, ahead of it. That is expensive even in the best conditions. In a restructuring megaproject, it becomes even more delicate because every early dollar spent on hidden infrastructure is a dollar not spent on something the public can see. But if the hidden infrastructure is delayed, visible progress becomes dangerous. This is why recent water infrastructure reporting matters. Industry coverage in 2026 reported that NEOM had canceled a planned desalination plant known as Moonlight, which had been planned at 150,000 cubic meters per day as part of broader restructuring. At the same time, NEOM continues to promote long-term high-capacity desalination, brine processing, and water reuse goals. Those two facts can exist at the same time. The ambition remains massive. The path is being adjusted. And for a water-dependent city, every adjustment affects the sequence. That brings us to the third revelation. NEOM's greatest water risk is not that desalination is technically impossible. The technology exists. The engineering knowledge exists. The risk is simpler and more dangerous. Demand could outrun the machine. Every growing city generates a demand curve. More residents mean more drinking water. More industry means more processed water. More landscaping means more irrigation. More hotels mean more cooling demand. That curve rises continuously. It does not wait. But NEOM's water supply has its own curve, and that curve moves slowly. Desalination capacity has to be tendered, financed, engineered, permitted, built, tested, connected to power, connected to the pipe network, staffed with trained operators, and brought online carefully. Power projects have to be ready, pipelines have to be laid, reservoirs have to be filled, wastewater plants have to be commissioned. Brine systems have to prove they can work beyond pilots and reach the scale of the desalination system they support. If the city curve rises faster than the water curve, the result is not theoretical. It is rationing, delays, construction bottlenecks, or a forced slowdown. This is the physical wall behind the financial wall. Money can accelerate many things. It can hire more people, buy equipment, and move deadlines forward. But water infrastructure has dependencies. A desalination plant cannot deliver water to a district that has no pipeline. A wastewater recycling plant cannot recycle water that has not been collected. A brine recovery system cannot claim environmental success if it has not reached the scale of the desalination system it supports. Everything must connect, and everything must connect in order. That is the engineering tension at the center of NEOM. This is why runs dry is not a prediction that NEOM has already failed. It is the pressure test. It is the question every arid megaproject has to answer before the opening ceremony. Can the water system scale at the same speed as the dream, without pushing the cost into the ocean, the grid, or the next phase? The public sees the mirror wall. Engineers see the sequence. Water first, power first, storage first, distribution first, wastewater first, brine first. Only then can the futuristic city behave like a real city. This is also why phasing matters so much. A shorter first phase may make the project more manageable. It concentrates demand, reduces immediate distribution length, and gives engineers a smaller system to prove before the full vision expands. But it also changes the narrative. The question becomes less, can they build 170 kilometers quickly? And more, can they prove the first piece works well enough to justify the next piece? That is a very different test. There is also a public perception trap here. When people hear that a first phase is smaller, they often assume the engineering problem shrinks in the same proportion. But utility systems do not shrink that neatly. Even a short first phase needs the basic skeleton: intake, treatment, power, storage, distribution, wastewater collection, brine handling, and emergency planning. You can reduce the length of the city. You cannot remove the need for a complete water cycle. And the test is not only architectural, it is hydrological. Now the whole picture comes into focus. Not the vision, the system. NEOM's water infrastructure is a machine with 4 gears. Gear 1, make water. Desalination is the source. Without it, the desert city has no reliable base. Gear 2, power water. Renewables are not decoration. They keep the water stream moving. If the energy system is unstable, the water system needs storage and backup strong enough to absorb the shock. Gear 3, move water. The line's geometry turns distribution into a mega infrastructure problem. Long pipes, pressure zones, pumping stations, reservoirs, valves, sensors, and redundancy. Gear 4. Close the loop. Wastewater recycling and brine recovery are what turn the project from a desert survival plan into a sustainability claim. When all 4 gears turn together, the concept becomes powerful. NEOM could become a working example of how a coastal desert city can grow without draining inland aquifers, without treating the ocean as a waste sink, and without making fresh water depend entirely on old fossil fuel systems. That would matter far beyond Saudi Arabia, because NEOM is not the last desert city that will ever need water. But when one gear slips, the whole machine feels it. Too little power and desalination slows. Too little storage and a disruption becomes a shortage overnight. Too little recycling and demand climbs faster than supply. Too little brine control and the Red Sea becomes the price of the city. Too little phasing discipline and demand outruns capacity. That is why the real NEOM story is not just about whether a mirrored city can be built. It is about whether a man-made water cycle can be built fast enough, cleanly enough, and reliably enough to support it. The future city does not begin with a skyline. It begins at the intake. It begins where seawater becomes drinking water. It continues through pipes, pumps, reservoirs, treatment plants, and sensors. It loops back through wastewater reuse. And it ends with a question most people never ask when they look at the render. What happens to the salt? If NEOM answers that question correctly, at scale, on time, without the Red Sea paying the price, it will not just be a city. It will be one of the most consequential water experiments of the 21st century. If it gets the answer wrong, the failure will not look like science fiction. It will look familiar. A delayed district, a canceled plant, a scaled-down phase, a construction site waiting for utilities, a city whose most futuristic promise is limited by the oldest constraint of all: water. NEOM may still become a new model for desert urbanism, but the model will not be judged by the mirror walls first. It will be judged by what happens every morning when people turn on a tap and expect something to come out. Because in the desert, the most important building is not the tallest one, it is the one that keeps the water running. And next, we are flipping the problem completely. Because in Japan, engineers faced the opposite nightmare. Not how to create water, but how to stop water from swallowing entire cities. Click the next video, How Japan Stops City Floods, and I will show you the giant hidden system protecting millions beneath the streets. Thanks for watching BuildPulse. The biggest builds are never just concrete and steel. What project should we break down next?